This video will recap the basic concepts for understanding parallel circuits. If you haven't watched the video called an electricity analogy, please do so first and then come back to this one, because I'll be using that analogy during this explanation. We have a very simple parallel circuit set up here. We have a battery, a 2-volt battery, and it's connected, as you can see, in parallel with a 4-ohm resistor, a light bulb, and then a second parallel branch here, a 4-ohm resistor as well. So two 4-ohm resistors in parallel and a 2-volt power supply. Just a reminder from the analogy, we're imagining people walking around a particular path, and as they come through the battery, our analogy says that they collect energy there, and we used energy drinks or monster drinks in our analogy. And a 2-volt battery, we can imagine that each person coming through here picks up 2 monster drinks on their journey around the circuit. Our analogy used an obstacle course for the resistor. It was hard to get through, and they used up some of their energy there. All right, let's start by considering current. From our analogy, current was the rate at which people passed a particular point. You'll remember the definition of current is just the rate of flow of charged particles, and so really it's just how fast these particles are moving around the circuit. I'm going to drag in an ammeter and just drop it in that part of the circuit. That's the main current, the total current flowing through the battery, and you can see this little ammeter is showing us that the current, the rate of flow of charge at that point is 1 ampere, which means 1 coulomb per second. Now, as we follow the current flowing down this part of the circuit, we can see that at this juncture over here, the current splits. Some of the charges flow in this direction, and some of the charges flow down in that direction. And you can see straight from the analogy, the rate at which these charges are flowing here is different to the rate at which they're flowing there. And that's because they split at that junction, and so we'd expect the current to be smaller here. Where we have two equal resistors, in this case both 4-ohm resistors, we expect the current to split equally. And so the current at that point over there is 1 ampere, and once it splits, we would expect half of it to go there. And so you can see there the ammeter showing us the current in that branch is 0.5 amperes, and in that branch down there is also 0.5 amperes. Once the current has gone through the parallel branch, at this juncture over here, the current combines again. You can see those combine there, and so in this part of the circuit, we would expect the current to be back at 1 ampere, and if I drop the ammeter there, you can see it's 1 ampere. So the key learning point here is that current in a parallel circuit splits. The total current would flow through the battery, and then in a parallel branch, the current would split. Let's now consider voltage. We have a 2-volt battery there, and so the voltage over there, if I bring in a voltmeter, the voltage over there is obviously 2 volts. Now, understanding voltage in a parallel circuit is tricky, and you need to be careful with this one. It's a common misconception, and you need to get this right to understand parallel circuits correctly. What I want us to do is to go back to the analogy now. Our analogy says that as a charge comes through there, it picks up some energy, and so as the people come past the table, they pick up 2 monster drinks. So if we follow any one of these charges, and imagine the analogy, they would have 2 monster drinks in their hand. Now let's follow this particular one over there. There it is, and it's choosing, that one over there is choosing to come down this bottom parallel branch. And if we followed that charge all the way through, remember, it would still have 2 monster drinks because it hasn't been through a resistor. If it goes through this resistor, in our analogy through this obstacle course, it would use up both monster drinks, because after it's been through this resistor, it's then going to go along here, back up there, and back to the battery. So it's not going to go through any more resistors. And so any charge coming along here would still have the full 2 volts, each coulomb, 2 joules of energy, and it would use it all up in this resistor. And so if we put our voltmeter over this resistor, we'll notice that it reads 2 volts. And that's because any charge coming through this resistor is only going through this resistor. It's not going through that resistor. If a charge comes down through this part of the circuit, it goes through the resistor, and then it goes back to the battery. And so it uses its full voltage over this resistor. In the analogy, it drinks both its monster drinks here. If we follow another charge coming down the main part over here, let's choose that one over there, and you can see it's now chosen to go along this path, this parallel branch. Now remember, it's still got its two monster drinks, and it's going to go through this resistor and then back to the battery. So it only goes through this resistor. So once again, it will use drink all its monster drinks, use all of its energy just in this resistor. And so if we check voltage over that resistor, we'll notice it's also 2 volts. So the key learning point here is that the voltage in a parallel circuit is the same over each component, and it equals the voltage of the battery. So if we have a 2 volt battery, the voltage over this resistor will be 2 volts, and this resistor will be 2 volts, and any other resistors connected in parallel will also be 2 volts. I've now changed the resistance of the bottom resistor to 8 ohms. So we have 2 resistors that have different resistances now. Let's go back and consider current. Because we've changed resistance and we've increased the resistance of this particular resistor, we would expect the overall current to change. And if I bring in an ammeter, you'll see that it's dropped down to 0.75 amps. The same principle applies. We still have a splitting of current, some going through this resistor and some going down through this resistor. But the key point here is that because this has lower resistance, it's an easier path for current to travel, and therefore more current will travel through this path than through the bottom path. And you can see just in the animation, these little charges are moving much more quickly than these ones down at the bottom. If I drop in the ammeter, 0.5 amps are flowing through that branch and 0.25 amps flowing through that branch. And you can see that's just half because the resistance is double. Notice still that 0.25 in that branch and 0.5 in that branch add up to the total current of 0.75 amps. And that total current is obviously also experienced on that side over there. So the current still splits in the parallel circuit, but more current will go through the path with lower resistance and less current through the path with higher resistance. Let's consider voltage again. Once again, as we follow a charge, the charge either goes through that branch and will use all of its voltage there, or it goes through that branch and use all of its voltage there. And so we would expect the voltage, obviously over the battery, the voltage remains at 2 volts. There we go, it's a 2 volt battery. We would expect the voltage over this light bulb also to be 2 volts, which it is. And it's independent of the fact that this is a 4 ohm resistor, because voltage has to do with the energy that the charges are bringing, and they're just coming through this one, dropping all their energy there, and then going back to the battery. If we check the voltage over this one, we expect it also, there we go, to be 2 volts, because once again, if the charges do come through this particular resistor, they have the 2 joules of energy per coulomb. They'll drop it all here because this is the only resistor they're going through, and then they're going back to the battery. So that confirms once again that voltage in a parallel circuit, just get rid of that, voltage in a parallel circuit is equal over each resistor, and also equal to the voltage of the battery.